Hi, good morning all. Thanks for coming. You know, when people had asked me about this talk, I said, no, it's quite a boring talk. I'm not throwing rocks at the crap we call RPKI, and I'm not going to tell you that IPv6 is just an undeployable mess. It's going nowhere. I'm not going to go down that controversial path. I'm just going to talk about the evolution of transport protocols until I listened to the last half hour from Alex. I could have been living in the 70s. In fact, I think I was. In that talk, there's this underlying theory that networks are scarce, networks are expensive, that somehow it's a resource that cannot be left to you users because you're scum. The network has to manage and allocate its precious resources at some considerable price to you because we're the professionals. And applications are dumb, intolerant, and insensitive. What a load of crap. The supercomputers of the 1970s take a small part of the compute power of this watch. We have moved on. And one of the things that's changed has actually been Moore's Law. Moore's Law, the doubling of processing capacity on chips every 18 months to 2 years, has been relentless for the last 50 odd years. We have moved from scarcity to abundance. How many folk have a gig to their house? How many folk are going to have it in the next 2 years? All of you put your hands up, right? Why do I need to resource manage a gig? What am I doing in submarine cables? Oh, a terabit or two. What am I doing in data centers? If I believe Nokia, it's a terabit or 1,000 or more. So why the need to spend your money effectively managing at a micro level for application transports that are not dumb, not insensitive, and frankly don't need the help that you're going to provide them in the network? Only a telco or a conspirator of telcos, vendors who market gear to telcos, would tell you that that kind of approach is meaningful in 2025. It's not. Everything has moved up the stack. None of the top 10 public companies in the world are transport companies. It's not AT&T anymore that rules the world. It's Google, it's Amazon. It's the folk at the application level. And driving that abundance is actually a change in transport. But it's not transport in bits on the wire. That's just commodity sewerage. It's actually transport end to end. And that's what I want to talk about. I talked about this as an evolutionary process, and of course you can't talk about evolution without Charles Darwin or Alfred Wallace. Some back in the 1800s, you know, that all of a sudden he saw the natural processes as a tension set, trying to resolve tensions by actually changing the nature of life forms to better adapt to their environment. And those pressures exist not only in biology, but also in technology. What I'm arguing about is that building a network for the 1980s, which is what I heard for the last 30 minutes, is trying to exercise how to build a kilobit network when your carriers are megabit capacity. Yeah, there's a rationing problem. Has anyone sat behind a kilobit link? I did, unfortunately, a couple of weeks ago, and my God, it was hell. I'm like, nothing works anymore. Nothing. So yes, we moved to megabits, we moved to gigabits. We're now doing TCP up at the level of gigabits to terabits now. It's not quite increasing at the same speed anymore over the last 10 years, but it's still an extraordinary evolution in how much capacity we can drive out of wires. Fibre wires these days, not copper on the whole, but how much out of wires. But the last, decade or so, it's plateaued out. It's not really getting much faster. Optical transmission folk, they're still on their KPAs. They're still going, we can do better than this. And quite frankly, optical transports are now looking at terabits per second inside single fibres because, they can. Latest evolution, hollow core. Can you imagine a hollow core in a fibre? It's only a few microns across. What happens when the cable snaps? How do you get the water out? I have no idea. I'm not sure they do either. But anyway, it's fast. And quite frankly, what you're seeing is the underlying optical transports are actually outpacing what we can do inside the sort of the engineering of speed inside silicon-based switching. There's sort of a massive capacity overhang. It's not scarce, it's abundant. So how do we use that abundance? By SRv6? Oh, bullshit. We just don't do it that way. We use TCP. All of you use TCP. It was the one spark of acute genius that actually put us all in this room and we all left the telco world. You know, that was it. That's the beating heart of the core of the internet. And it operates within two modes, efficiency and fairness. Efficiency. Idle bandwidth is an unpardonable sin. Don't ever leave spare capacity on the floor. So to be efficient, minimize packet loss, stop reordering as much as you can, and don't leave unused bandwidth on the table. That's what the transport protocol is trying to do all the time. You need to run at this level. No. If there's spare capacity in the network, I'll use it. And so will you, and so will everyone else. The other thing is fairness. It's not a conversation between an application and the network. The network is not part of this conversation. It's a conversation between your transport and my transport. It's a conversation between competing versions of TCP, where on average, we equilibrate with each other. It's like your drive to work, assuming you are going back to work these days, in a car. The traffic equilibrates with each other. It's really hard to go at 200 miles an hour down the freeway to the airport in Melbourne in the morning, right? Because everyone else is in the way. You end up going at the same speed as everyone else. You self-equilibrate. That's what we expect from TCP. It's a flow control problem, isn't it? Because what you're trying to do is to get each session to exert the same pressure on all the other sessions across all these sessions. If you manage to get that just right, the outcome, without any network assistance at all, is fair across all the sessions at once. That's what we mean by fairness. And brilliantly, TCP largely achieves that. How? Source routing. Oh my God, I last heard that. Seriously, it was in the 70s. Jeez. I thought, I'm getting old, and you know, these ideas are coming around, or they were bad ideas then, and they're bad ideas now. I can't get over it. TCP is a self-clocking feedback protocol. The way it works is actually you send packets into the network, ACKs come back. Every time you get an ACK, that tells you a packet has left the network. So there's a packet space you can fill with the next packet. And as long as you pace like that, you can maintain a steady stream of packets. If you send at a rate that's slightly faster than 1 packet per ACK, you're gradually increasing the pressure on the network. If you send at a rate that's less than 1 packet per ACK, you're decreasing the pressure on the network. But basically, you tune what you send, to the ACKs that are coming back to you at the same time. That's, the underlying element of how TCP actually works. So how fast are you meant to go? I don't care what the network says. I really don't. The bastards are probably lying anyway, because, they do. Instead, you use rate adaptation. You go as fast as you can and don't bring the network down in a screaming heap. And that's the only rule. So what you do is you probe into the network, gradually increasing your pressure on the network until you get feedback that goes, whoops, you went a bit fast, back off a bit. Now, in essence, that's what every TCP does, every one. And we've experimented with a lot of them over the years. The one that's been generally used, but not universally, has been AIMD, where your increase is gentle. And this worked well in low-speed networks. It's worked well for about 20-odd years. Less relevant in the gigabit world. It's harder to make this work because there's just so much headroom. But you increase your sending rate conservatively. And you keep on adding that pressure, and oddly enough, the wire will fill, the queues will fill, and then a packet will drop off the queue. Oh, disaster, a packet's lost. It's IP. Every packet's an adventure. Get over it, dude. You know, lossless Ethernet in AI data centers. I thought it was so cool, but so unreal. Once you get packet loss, it's not a disaster. It's just a signal you were going a bit too fast and the queue overflowed. Back off. Back off quite quickly. In AIMD, reduce your sending rate by 1/2. So quite a dramatic back off, and then do it again. How fast should I go when I start? Oh, foot flat to the accelerator, flat to the floor. Double your sending rate every round trip time. Sooner or later, you'll saturate the lot and you'll get a packet drop. You're going too fast. Somewhere between nothing and what just happened is where you need to be. And that's where TCP kind of starts up and finds the initial point. There's a classic picture. You've all seen this. If you haven't, you've been looking at the SRv6 textbooks. Turn them off, shut them down, run away, have a look at this picture again. This is the way we drive networks. The TCP packet format doesn't change, but the control algorithm does. What are you trying to do? A, don't be a wimp. If you're not aggressive as everyone else, you're in the parking lot. You're never going to get bandwidth. You need to exert the same pressure as everyone else. If you really are searching for niches and corners, try and exploit opportunities that other TCPs aren't exploiting. That's fair. But, you know, don't completely destroy the network because we all die. So don't push too hard. It's not quite as simple as that because the world is not fully fibre. We got stuck into IP over radio, and radio is a horrible environment. The bit error rates go through the roof, and you get non-congestive packet loss. And you're kind of going, what happened to that packet? I thought I was going quite slow. And the answer was, yeah, you were, but you know, someone walked behind a tree. Oops. And you take this, and I have talked here about Starlink, and you take it one step further and try and communicate with something that's zooming through the sky at 27,000 kilometres an hour. And you're trying to use a dish that's about yay big, and no wonder packets are spewing everywhere. Huge jitter, huge problems, and that's certainly a challenge for any transport. Terabit is a problem. Really, really high speed. Because if you're increasing by basically one segment every round trip time, it'll take about 3 years to get to a terabit bandwidth. No one lives that long, right? So somehow you've got a sense that you're in a really big network and push an enormous amount of data into the network extremely quickly to take advantage of it. It would be good to do equal cost multipath because if there's bandwidth, go and use it. Much harder for end-to-end. But if there is equal cost multipath being used, TCP should adapt to it. It should be tolerant of small amounts of packet reordering, and it is. And of course these days, because 90% of what you ship out to customers and you get paid for is video. And all of you are trying to cope with the Netflix pulse. Oh, the buffer's low, whang. And the server, whoops, bashes the microphone. The server pushes as fast as it can from a big data center right through the network, and which causes a huge impact on your queues, on everyone else. And trying to smooth out that session pulsing is almost an obsession these days from the video streamers. Because if they can get that right, the access network operators like you will stop complaining about video smashing your networks periodically. So yes, we're aware of that, and it's certainly a challenge. One of the ways around this, change the way you increase pressure. And this is one that's been adopted by Linux, and therefore as Linux largely rules the world, Linux is cubic these days, and cubic doesn't use a linear rate increase. It tries to go very quickly up to what it senses is the optimal point, and sort of sits there around I've filled the wire and now I'm pulsing against the queues as long as it can. But if it senses that nothing's gone wrong and no packets got lost, it kind of goes, right, all bets are off. I'm going to resume a massive rate increase because whatever's gone away is cool. I'm just going to reoccupy the space as quickly as possible. almost everyone uses cubic. Queue formation is slightly different. The queues tend to remain sort of higher than normal, but it certainly gives reasonable results. Reacts quickly to available capacity, which in a day of gigabit networking is exactly what you want. It can sit there for extended times doing that, and certainly will handle video pulsing. Long fat pipes work. Buffer bloat is a bit of an issue, and we'll talk about how we try and get around that. It's not the only sort of kit on the block, but it's certainly the most dominant one because of Linux. There's a whole bunch of these subtle variations. Akamai use fast, and we'd like to know what's in it, but it's proprietary and they've published nothing. We think it's delay-based, but we're not sure. The other ones around that I haven't mentioned, I will, which is BBR, which is the other kit on the block. Thank you. We will see. So, buffers. There was this rule out there that you needed to provision your buffers at exactly the same capacity as the link you were driving. So if it was 1 megabit per second and the link was 1 second long, you needed a megabit of buffer, right? In other words, you dimension your buffer at exactly the same rate as the link you're driving. So what this means is, if I stop sending for 1 round trip time, if the queue was full, it will drain, because it had 1 round trip time of data inside it. So normally, and I'm sure most of you do, even if it wasn't a deliberate decision, dimension your queues inside your network against the size of the link that you're driving. Big links, big buffers. Short links, smaller buffers. Pretty standard stuff. The problem is, if you get it wrong, people do suffer, users suffer, or you suffer. If it's too big, what goes on is the link fills, you pause because you've got a packet loss, but the buffer is so big, it never drains inside that pause interval. So the queue constantly remains with some stuff in it. Now, that's the same as putting in a delay loop. And so you're going, I have this really fast path from A to B, Perth to Melbourne, but I never get a faster round trip time than, 100 milliseconds. It's a queuing problem, and it's caused by the buffers being too long and the queue being permanently full, causing delay. So if you over-dimension, if you get it wrong, you're just causing delay. If you under-dimension, and that was the first example with ATM and why it got such a horrible reputation in the internet, it had no buffers. None. It was a high-speed interface, and they were few and far between back then, but no buffering. So as soon as you tried to push against the network, it dropped packets. Oh, back off by half. And so you could never get capacity through an ATM switch because it had no buffers. Short buffers are as big a problem as too big. So what's the right size? Bandwidth times round trip time. And that's what most of you do. If only you had one customer and one flow, the theory would match the practice would match the theory, and everything works. It doesn't. It's not like that. Because you don't deal with one customer, you deal with hundreds of thousands, even millions of them. And all of a sudden, all of these simultaneous flows cause a different kind of problem. All of them are doing this flow control. Now, if they synchronize with each other, the practice still holds. Because if they're all pulsing at the same rate, you still need the size of the buffer equal to the size of the link you're driving. If they're precisely out of phase, if they're just jumbled, then the common buffer requirement actually reduces, and you need shorter buffers. In actual fact, in all of your networks, you should be looking, using your flow metrics, to see what kind of large-scale flows you're simultaneously supporting through your network. And you can divide your buffer size by the square root of that number and say, well, that's the number I need in my buffers. So to get 1/n of the resource, you don't need large buffers. You need buffers that are proportionate to basically the amount of flows that you're supporting through that, inversely proportional to the square root of the number of those flows. God, it's a 20-year-old paper now. Aren't we all getting old quickly? So let's look a bit more about these buffers, because they're the key to how the transport protocol at the application level matches the behaviour of the network, right? So buffers smooth out bursts. I send data as fast as I can. At some point, I can't push it at that rate. That pulse has to be absorbed into a buffer and then eked out at the pace of the next link. And the second thing is, if I've got 100 input links and one output link and a packet arrives at all 100 links at the same time, the buffer needs to take 99 packets, to get over that sort of simultaneous multiplexing load. So they serve two roles. How do you make life easier on the network and get better throughput? If you serve traffic and you haven't got that configured, you're foolish. Pace your sending. And all modern host systems have this pacing control. Because if you don't pulse, you're not relying on the network to kind of absorb your sins. You just gently pulse through the network, relieving the buffers of that pressure. So whatever your favourite network is that you use for your servers, turn on pacing, because pacing is really important to make networks sing and dance. And quite frankly, if they all paced, the buffer requirements are actually really, really small. Why does this matter? Well, memory is not getting any faster. We might do 1 trillion gates on a chip, but the clock speed is not really changing at the same rate as the number of gates. Memory speed is not scaling at the same rate as transmission and switching. And quite frankly, the speed of memory is almost flat, with the speed of processors is only flattened out more recently. So let's get down into ASIC design for just a second. Amazon Lincoln said 1 chip. Just 1 ASIC in that box. Now on that chip, assuming he was telling the truth, is both the switching fabric and the buffer memory. So on that chip, he's got between 16 to 64 megs of really high-speed memory, and that's all he's got. Now, you can go, okay, I'm going to use external memory chips. I'm going to drive it out through an I/O bus and so on. The problem is, even that external interface takes up space on your ASIC, and it's slower. It's inevitably slower. So what you really want to do is to make sure that you design your network to be able to put this stuff onto 1 chip. Same as Amazon. And that means your buffer requirements for individuals, switching requirements, are between 16 and 64 megs on the chip itself. Now, that, between 20 and 60% of the chip real estate is devoted to that role. So if you can reduce the amount of memory you're using to drive your network, you can actually increase the switching capacity, which is actually where you want to make your money, because you then more interfaces per chip. What is wrong with this microphone? Be gone. You know what I'm saying. The next thing is trying to talk about flow states, because I've got this end-to-end flow state, and what I'm trying to do is avoid leaving bandwidth on the table, underutilise, avoid bringing the network into congestion, collapse, saturated. I'm just trying to sort of put it at an optimal point. Now, I've talked so far about reacting to loss. Loss is like a traffic accident that's really quite bad. It's very hard to drive away from a good smash, right? You've lost a packet, that's a disaster. What's actually gone on is that you've driven the network where you've filled the wire and you've filled the queue, and the queue is now at overflow. You've reached the end point. I'm now spewing packets off the end. That's not where you want to be. That's the worst possible place to recover from. Because I'm getting packet loss, I'm no longer getting a feedback control signal. I've lost contact with the other end. Loss is perhaps the worst possible signal to derive your control. What you want to do, in the best of all possible worlds, is find the onset of queuing, the point where you've filled the network and you're just at the point of overfilling it and putting pressure on the buffer. So the bottom point is the optimal operating point, where effectively you've got the maximum throughput you're ever going to get, and if you push any more, it's just going to fall into queues and not give you any answer. So how do you detect that? Geez, I'm going to move a lot faster. You're going to detect it by using the network to tell you when queues are forming. Explicit congestion notification. Isn't that a great idea? It should do. It's 30 years old. The router says, I'm getting a little bit congested here. Queues are forming. I'll mark the packets. And then TCP says, let me carry that back to the centre and get them to back off. It's a nice idea, but quite frankly, as I said at the start, application folk have lost patience with the network folk. They think the network folk are living in another decade in a world of reality that talks about RSVP and SRv6 and bullshit like that. And quite frankly, ECN is not deployed at all. I measured it a few months ago and it's down around 2% and it just doesn't work. So nice theory, you can't do this. So you've got to do it differently. You've got to measure the network at the point at which queues are starting to form. So this is where we get to BBR, which is a piece of inspired brilliance. What you actually do is not gradually increase your sending rate. Hold it steady for 6 round-trip intervals and then bring out the mallet. 25% oversend, and in one RTT, hit the network hard with 25% more packets than you were sending in the last round trip. And the next round trip, back off by 25%, few, and measure the round trip time of the point where you were oversending. If the network simply absorbed all that and said, same round trip time, you go, right, fine. Queuing is not happening, there's more wire capacity, open the floodgates a bit more. If the delay increased at that pulse point, right? If the delay increased, it's sort of, right, that was all in queues, I'm optimal. And this is a simulation, but you can see what's going on. It very quickly finds the point where queues are forming and just continually just pulses 1 round trip out of 8 to see if you're at the optimal point. The queue occupancy down the bottom is not a big queue, it's a tiny queue. And you're pulsing into the queue, you haven't got steady state occupancy. Is it polite? This is a graph of cubic versus BBR. And everyone will say, well, yeah, it is an evolutionary war and BBR is winning, you know, like reptiles versus mammals like winning, you know. BBR is very, very, very unfair to non-BBR sessions. And that's why it's kind of, oh, you're using BBR, frowny face at you. I'm kind of going, it's my traffic. I'm enjoying this like crazy. You should use it too. But anyway, yes, it's not very polite. So what do we have? A very diverse mix of transport protocols, a whole bunch of various models, a whole bunch of queuing disciplines, a whole lot of buffer size deployments, and even some form of sporadic ECN marking. But what it does show is that we're solving our problems on how to fill high-speed networks at the endpoints. And the reliance on complexity and crap in the switching forms of the network is just making a bonfire of your money. It's not doing anything productive. It's just a waste of everyone's time. Rip it out and simply do stateless switching, and you'll probably find your life will be easier. You won't be doing late night calls on something failed in SRv6, and users might actually smile at you. And I think that's all I had to say. Oh yes, we don't know much about this stuff. We're still learning. There is much more to do. A lot of even our cherished theories now about how to do packet-based stateless networks are probably not exactly right, but that's good. There's always more to do. Thank you.
Thank you, Geoff. Do you want to do one question?
Is there one question?
Is there one? I can only see one.
Wasn't Alex?
You missed out on Quick.
No, Quick is just TCP with encryption because the network bastards didn't stop there. They started looking inside the IP packet to find the TCP packet and started mucking around with the control bits. Quick doesn't change the elements of control very much at all. It's still basic buffer-based management. And Quick with BBR really does fly, I can assure you. But beyond that, Quick just says to the network operator, even if you try, there is nothing to see. Good luck. So the battle lines, I think, have been drawn by the application folk. We've run out of patience and tolerance It's all over. They really are just commodity providers. And the vendors to that, you're never going to make money out of your network in large heaps anymore. Those gold bars have disappeared. They've all gone to Google. Thank you.